Hi everyone, welcome to part 3 on our video lectures for section 8.4 dealing with trigonometric substitution. In the previous two sets of videos, we went over the idea behind trigonometric substitution and practiced a couple of examples. In this video, we're going to be taking a look at two more examples and one application problem. So let's go ahead and begin here. Alright, so beginning with this problem, we have the integral from 0 to 1 of x over x squared plus 1 raised to the 3/2 power. Now, this one here looks very similar to the first problem that we're working on. However, there's one big difference. The previous problem only had a 1 in the numerator, whereas this one here has an x in the denominator. Now, how will this affect our problem? Well, I would say that it's going to affect it in a very nice way. Do you guys see how? Well, if I take a look at my denominator here, I see an x squared plus 1. Now, it's a sum of squares here, but there's even better news. I'm going to do the following. I'm going to go ahead and let u equals to the x squared plus 1. So then that means that our du is going to be 2x dx. Oh, well, I actually have an x on the numerator now. So this problem can actually be done simply with a u substitution. There is no need for a trigonometric substitution. Now, the reason that I'm including this problem here is because I don't want you to get fixated on one particular approach. Remember, any integral that you encounter, see if you can solve it in the easiest way possible. Sometimes a u substitution can work. If a normal u substitution doesn't work, well, that's when we try the other approaches, maybe like an integration by parts problem, or a different technique involving the trigonometric integrals, or, as we're doing right now, a trigonometric substitution. So this problem here can be done with a normal u substitution, so that's what you would do. Now I'll let you guys finish this one on your own, or this one on your own, because now I want to move on to another problem. So take a look at this one here. We have the integral of 1 over 4 plus 9x squared. Now, does this one look a little bit familiar? In fact, some of the other integrals might have looked a little bit familiar, because we've been working with problems involving the square root of either a sum of squares or a difference of squares. Those were the problems that were involving the inverse trigonometric functions. Now, some of the inverse trigonometric functions that we encountered before, I just gave you the formulas to figure them out. This time around, though, now that we have the trigonometric substitution tool at our disposal, we don't really need to memorize any formulas. We can just draw triangles. So for this one here, you might recognize it as an arctangent problem, and it is, but let's see if we can get the same result with a trigonometric substitution. Alright, so for this one here, what do we notice? Well, I see that on the denominator I have a sum of squares. Now, it's just a sum of squares though. We don't have a square root. Well, we can be a little bit clever here and say that, well, technically we could make it have a square root because we can think of 4 plus 9x squared to be the same thing as the square root of 4 plus 9x squared squared. Okay, well, now it becomes a problem that's similar to the one that we did in the previous video, where we were raising it to a 3/2 power, but we had a square root somewhere in there. So, now that we have established our square root, let's go ahead and draw our triangle. Alright, so here is my triangle. Now let's go ahead and define the C, the A, and the B, as well as our angle theta here. Alright, so for the C here, we have the square root of 4 plus 9x squared. Now what about the A and the B? Well, I'm going to go ahead and define my A as a 3x and my B as a 2. Now, the reason I'm doing this is because, well, if I know that A is the same thing as 3x, well then we can use the tangent of theta and define it as the opposite over the side adjacent to the angle, which would give us an x value of 2/3 times the tangent of theta. And this is a much simpler formula to find a derivative, so we can figure out the differential dx in terms of d theta. The differential dx here is going to be a 2/3 times the secant squared of theta times d theta. Okay, so we've gotten our x, we got our differential dx. Now let's see if we can go ahead and figure out our cosine, because we have the sine adjacent here. So the cosine of the angle theta is the side adjacent to divided by the hypotenuse, which is the square root of 4 plus 9x squared. Okay, now let's take a look here at our original problem. So the original problem was the integral of 1 over 4 plus 9x squared, which we rewrite here. So I'll rewrite it here in terms of that, or in terms of this new form. So we're going to have here 1 over parentheses the square root of 4 plus 9x squared. And we were squaring this one here and dx. Okay, now here comes the substitution. Now, if I wanted to have only a 1 over the square root of 4 plus 9x squared, going back to the way that we defined the cosine, I'm going to go ahead and multiply this one here by 1/2. So we have 1/2 times the cosine theta is equals to 1 over the square root of 4 plus 9x squared. Now, since in this problem we were squaring the square root, I'm going to go ahead and square both sides. Square both sides. So then we're going to have 1/4 cosine squared of theta is the same thing as 1 over 4 plus 9x squared. And that's exactly what I'm going to go ahead and use when I'm rewriting it. I'll rewrite it here as 1/4 times the integral of a cosine squared of theta times dx, which we got to be 2/3 times secant squared of theta d theta. Okay, now what can we simplify here? Well, I'm thinking that we can probably simplify the multiplication of 1/4 with the 2 on the numerator for the other fraction. So that's going to give us essentially a 1/2 times a 1/3. So that's going to be a 1/6 times the integral. Now what happens here with our trigonometric functions? Well, we are multiplying a cosine squared times a secant squared. So this one's actually also cancel. Okay, well, what gives then? Because now we're just left with a d theta inside our integral. Now that's actually very good news, because now we can go ahead and rewrite this one here as 1/6 times the integral of d theta. Well, that one here is just theta plus c. Okay, so now we're back to getting a theta. That's not a problem because, well, we've gotten a theta plenty of times before in this set of videos. So since we defined tangent theta as 3x over 2, we can go ahead and take the arctan of both sides, or the tangent inverse. So I put here tan inverse of both sides. That's going to give us a theta. Put the theta in orange. It's going to give us a theta here is equals to the arctan of 3x over 2. So this means here then that our final answer is going to be 1/6 times the arctan of 3x over 2 plus c. And there we go. Now what we just did right now was essentially derive the formula for integrals of the form du over a squared plus u squared. This one here, if you recall our previous set of videos, in fact, I'm going to go back to section 7.5. So taking a look at section 7.5, oh, well, there we go. This is the integral that we just derived. Now, truth be told, this one's and this one's, you can actually now derive all of them using trigonometric substitution. So excellent news. We don't need to memorize any formulas anymore. We can just use right triangles and trigonometric substitution. Okay, now let's take a look at our last problem here. Now this one here is more of a slight application problem where we're trying to find the arc length for the function f of x equals to x squared on the interval from 1 to 3. Alrighty, so now we're back to an arc length problem. Now remember, the arc length is given by the following formula. L is equals to the integral of the square root of 1 plus the derivative of f squared. And we are evaluating this integral from a to b. Okay, so in the context of this problem, we have our f to be the x squared. So then f prime is simply a 2x. and we're evaluating this one here from 1 to 3. So we're going to be working with the integral from 1 to 3 of the square root of 1 plus 2x squared dx. Oops, I missed the dx here. There we go. So this one here is going to give us then the integral from 1 to 3 of the square root of 1 plus 4x squared dx. Okay, so how can we do this problem? Now, notice for this one here, things are looking a little bit different because, well, this time around, we don't have a square root in the denominator, but that's perfectly fine. It doesn't really matter where we have a square root. We just need to notice that you have a sum or difference of squares. And in this case, we have a sum of squares. Okay, so it looks like, once more, we are given the hypotenuse for a triangle. So let's go ahead and draw a triangle. Okay, so we are going to have our C, which in this case is the square root of 1 plus 4x squared. We're going to have our A, and we are going to have our B here, as well as the angle theta. Okay, so what should be our A and what should be our B? Well, hopefully you guys are feeling more comfortable now, and you get to pick your B to be a 2x and our A to be a 1. Okay, so now that we have this set up, let's go ahead and figure out, okay, which trig functions can help us. All right, so for this problem, since we have the square root of 1 plus 4x squared, I'm thinking that the the trig function that can help us the most is probably a secant. Now, why a secant? Well, if you think about it, the secant of theta here can be defined as the hypotenuse all over the side adjacent, which in this case is just a 1. So this problem here is just the integral of a secant of theta. Now, what about the dx? Well, just as we were doing before, I'm thinking that we can probably use the tangent function in order to avoid dividing by the complicated hypotenuse here. All right, so we're going to have then the tangent of theta is equals to 2x, side opposite, divided by the adjacent, which is the 1. So it's just the tangent theta is 2x. Okay, not too bad, which means that we can easily get our x. X is equals to 1/2 times the tangent of theta. Now getting the dx, we're going to get dx is equals to 1/2 times the secant squared of theta d theta. Okay. Alrighty, so let's go ahead and put everything together. Actually, before we do though, well, since we are going to be evaluating at different values of x, let's see what those values of x would be in terms of theta. So I'm going to go ahead and get the theta here. So let's see, put the theta and let's go with orange. All right, so if we know that tangent theta is equals to 2x, then that means that theta is equals to the tangent inverse of 2x. Now theta evaluated at 3. Now this one here unfortunately is going to give us, well, not the best of values. So this one here, theta evaluated at 3, so it's going to be the tangent inverse of 6, and the theta function evaluated at 1 is going to be equals to the tangent inverse of 1, which we've done this one here a couple of times. It's just going to be a pi over 4. So, well, not the best of limits of integration, but let's see what we get here. So substituting everything now into our integral, we're going to have the integral going from pi over 4 to the arctan, we'll put here arctan, of 6. And this one here, what's the integrand? Well, we said that the square root of 1 plus 4x squared was the same thing as secant theta. So put here as secant theta times dx, which we saw was 1/2 times the secant squared of theta d theta. Okay, so this one here is going to simplify as 1/2 times the integral from pi over 4 to the arctan of 6 of a secant cubed theta d theta. Oh, well, look at that. It's the integral that we did in class. Okay, so I'm just going to go ahead and take the results that we got from our previous lecture. And it's going to be the following. We're going to have here a 1/2 times a 1/2 times the secant theta times tangent theta plus 1/2 times the ln of the absolute value of secant theta plus tangent theta. And we are going to be evaluating all of this at pi/4 and the arctan of 6. And oops, I got a mistake. Maybe you guys caught it as well. Now, when we were evaluating the lower limit, so when we were evaluating theta at 1, well, remember tangent was 2 times x, so this one here should have been, and I'll correct the other one as well. Well, this was wrong, but I'll clarify it here. It was 2 times 3, so it was the tangent inverse of 6, and this one here is the tangent inverse of 2 times 1, which is the tangent inverse of 2, which makes things matter worse, because this is changing our limits here into values that are not that nice. So here we have the arctan of 2. So we're changing this one here to the arctan of 2. Now, once I plug everything here into my calculator, I get approximately 8.268. Okay, so this one here, I would say that the integration itself wasn't too bad, but once you actually got to evaluating the definite integral, then that's where things, yeah, they took a turn. But hey, that's what calculators are for, so we get an approximate answer here. It's perfectly fine. Now, if we actually got the exact answer, it wouldn't have been all that bad, since there were certain identities that we could have used, and in fact, since we had a tangent, and we were evaluating, well, we were evaluating the tangent at some arctans. They would have canceled out, so some things would have simplified, but it wasn't the easiest of problems. Alright, so this concludes our video lecture for section 8.4, dealing with trigonometric substitution. And again, I want to emphasize that there is no need to remember any particular formulas for this type of integrals. All that we need to do here is create a right triangle and use it to define our algebraic expressions in terms of trigonometric functions. Okay, now with that said, as usual guys, if there's any questions or comments, please let me know and I'll be there to help you. Alright, have a good one.